When we first open a game, we usually see a nice progress bar while everything loads up. But behind the scenes, it's not as simple as it looks. Today, we're going to introduce a method that has proven itself for managing the game startup, known as single entry point. In Unity, the easiest way to start a game is to fill the scene with game objects. And when the game starts, each game object is responsible for its own flow, because this way, we get separation between objects and clear division of responsibilities. For example, the player might load a weapon for itself. The UI will display the level number, and the enemies spawner will spawn enemies around the player. But then, problems start to pile up. The first problem is that it becomes difficult to sync one event after another. For instance, what if we want the player to start at a random point, and only after that the enemy's spawner will create enemies around the player? In such a case, even if we write the code that places the player in awake and in the enemy's spawner, the code that spawns enemies in start, it won't be good enough. Because the moment we need to wait for one more thing, like displaying the level number for a few seconds before the round starts and the enemies spawn. Playing with start and awake won't work anymore, because these processes depend on each other and need to happen in a specific order. And of course, as the game grows, more processes like this will pile up, like server requests that we'll need to wait for, initializing third parties, transitioning between game states, initializing features, loading bundles, and the list goes on. Another issue is that as the game grows and the scene fills up with game objects, when loading it will just get stuck on a black screen until everything loads. So to avoid this, we might want to display a convenient loading screen while objects load in the background. But it won't be simple to know when to turn it off, because again, everything happens simultaneously without a unified flow that lets us know at which point the loading is done. We can think of this process like a chain reaction of dominoes. If it starts from multiple points, there's potential for collisions, and parts will need to wait for others. But if, like in dominoes, we start from a single point, the process will be synchronized and smooth, and this way, we can extend it to sub-processes in an orderly fashion. Great! Now that we understand the problems, let's walk through the steps to solve them. The first step is emptying our scene. In Unity, this is done as follows. First, we'll drag all the objects from the scene and turn them into prefabs. Then, we'll delete them all from the scene and empty it completely. And yes, without leaving anything behind, because this comes with several advantages. The scene will load as quickly as possible, and the user will experience minimal black screen time. When the scene is completely empty, it's definitive, leaving no chance of reverting to a messy scene with many objects. In a team, this prevents conflicts. It forces us to save all objects as prefabs, which reduces the chance of two people working on the same prefab simultaneously. And even if it happens by mistake, the conflict is small and not over the entire scene. Future developers will easily identify where the flow starts. We'll dive into that more later. But wait, what if we want to design a level in the scene? How can we do that if it's empty? For that, it's recommended to separate our game into multiple scenes. For instance, we can create an independent scene for the level, where we'll design the environment. And then, we can load it using code on top of the main game scene. So after all that talk about keeping the main scene empty, we'll admit that we might have bent the truth a bit, because the next step is to create one game object with one script, and we'll call it, for instance, Game Initiator. And as the name suggests, it will be the entry point to our game. In the Game Initiator, will be the only start method in our game from where the flow will begin. We'll want the flow to be asynchronous, so we'll change the start method to be async. This way, using the UniTask package, we can conveniently wait using await. And of course, we can also do this with coroutines for those who prefer. Since now the flow starts from the Game Initiator, we'll go back to our other scripts and remove the independent logic that happened in each of them, and make their methods public, because they will be called from outside. Awesome! So now all that's left is to go back to the Game Initiator, call these methods one after another, and we're done, right? Not so fast. In a small project, this might be true. But to support a larger project, there are a few more steps in the game startup process we need to cover first. The next step in the process is the binding step. where we bind each class to its corresponding value. For instance, in our simple example, we'll write a serialized field for each class. And this way, we can drag each of the prefabs we previously created into the game initiator, and it will receive references to them. The beauty of bindings is that now we have one organized place that holds all the game's references. For example, if tomorrow we'll want to link a different loading screen, it can be easily swapped in one place. Next, we'll create an instance of each class in the scene using the instantiate method. And of course, we'll keep their references for later. Let's turn on the loading screen now, because we'll want it to appear as soon as possible before continuing the flow. Now that we have references to all the classes, some of them might need initialization. This brings us to the initialization step. This is where we initialize any service that needs to be set up at the start of our game. For example, if we had a third-party analytics service, or maybe we're using Unity's new game input system, and there's no choice. They need an initial startup to function, so we would initialize them here. But in our example, we have nothing, so we'll leave this empty. After initialization comes the creation step. Here, we load the heavy objects into our scene. Usually, they are loaded asynchronously, whether through resources, asset bundles, or addressables. But in our simple project, we'll just instantiate them directly. So let's create the background, the player, the level UI, and the enemies. But to create the enemies, notice that the creation step forces us to do something interesting. In the enemies spawner, we'll have to split the spawn enemies around point method into two parts. One for creating the enemies, which will be called now, and another for placing them around a point, which will be called later. So thanks to this side effect, we discovered that the spawn enemies around point method previously performed two tasks which are unrelated. One of creation, and another entirely related to game logic. Which of course is bad because each method should do only one thing. Now, after creating all the objects, we need to prepare them for display. For example, loading the relevant game data for them, positioning them, or changing their appearance. But in our case, we'll prepare the game as follows. We'll move the player to a random position and give him a starting weapon. And now, it's simple to spread the enemies around the player. Also, we'll disable them for now, because we want to display them later, only after the UI animation finishes. Finally, we'll update the level text to the current level. Notice how we're achieving even more decoupling in our code. Classes that used to have references don't need them anymore. For example, the enemies spawner simply places the enemies at a certain point it receives without knowing about the player. And the level UI simply takes an int and puts it in the text without being aware of the level manager. Great! Finally, our game is ready, so it's time to close the loading screen. And we can even do this with our own custom disposable, like this. For those unfamiliar, you're welcome to watch our video on iDisposable. We can also easily support a loading bar, advancing it slightly after each line of code. So can we start the game already? Yes, now we can. So let's start the game by writing the flow we wanted. All that's left is to display the UI animation. Wait for it to finish, and turn on the enemies. Isn't it beautiful that, thanks to the step separation, we completely isolated the game logic into two simple lines? Great! We've lined up our domino pieces, and now the flow is synchronized, readable, and clear. Plus, even if one of these lines suddenly requires us to wait for it, it's super easy to support this. We just need to make it asynchronous and add a wait. So, we've shown here how to start a game in a small and simple example. But how does the flow look in a big real game? How should the responsibility be divided among classes? Because it wouldn't be responsible of us to write all the loading code in one big class. Quickly, we'll reach an enormous amount of references to maintain. So, unfortunately, this is a large topic in itself, which we'll dive into in one of our future videos. Enjoyed the video? Share it with your friends, and show us that love with a thumbs up and subscribe. And thanks a lot for watching. We hope to see you soon in another Practic API video.